previous project that started some years ago with my colleague from Brno. We were trying to use some experiences we gained together with Dominic and Martin in previous programs with solid ceramic laminate. So we're trying to adapt or use the coupled criterion for prediction of failure of ceramic foams. So let me show you some pictures. So the motivation was to predict fail force or strength of such porous ceramic structure. In this case, produced ceramic foam using the 3D printing technology from alumina material. This foam was composed of carbon cells, and we tried to we tested the compression, and we tried to predict the strength of such foam using the coupled criterion. So the aim was to predict both the critical force necessary to break the specimen, and also try to see if we can predict also the fracture surface. Okay, so there are several approaches or different approaches how to deal with these porous ceramic materials and porous, generally porous materials. You can estimate the strength of such foam using very simple analytical estimations from Gibson and Egby relations. They are based on the relative density of the foam. You can have some first estimations, so then you can use some 2D analytical beam models or 3D imaging in some specific cases to also estimate the strengths. Then what we did in the past also to use the 3D beam element based finite element models, where you model the strats of the foam structure using beam elements. But this is also not very precise because you have not precise connection of the strats as in reality. So at the end, you have the final possibility to use the 3D realistic solid FE models, where you create the model based upon some CT scan of the real foam structure. Of course, this last possibility is the most complex, since you have really you need to model every detail using fine elements, and it's quite demanding on computational time. So now I would like to show you how we can predict the strength of the foam using this most complex way. Okay, so this was the geometry of the cell. It was a Kelvin cell of diameter 1.6 millimeters. We created an array of such cells, and this formed the final foam structure. This was printed using the 3D printer and then tested. So we created the same model with the same geometrical characteristics, and here are the material properties of alumina used in the simulation. So further. So before we could apply the coupled criterion, we had to know where is the critical location where the potential failure can occur. So we did preliminary simulation where we loaded the structure by displacement, and we took a look on locations where concentrations of stresses are present. So here, these corners or connection of strats, we can expect that it will be the first place where the crack will initiate. This was also confirmed by the microscopic analysis of the broken foam structure from the experiment. So the failure comes from this corner, it goes a little bit inside, and then kinks so that the strat breaks. So this was the first necessary calculation. So now how we can apply the coupled criterion to predict the failure of the whole foam structure. course, we have many fracture surfaces because there are many strats, and to break the foam and to determine the strength, you have to break really a lot of strats. So it's not possible to have realistic crack in all positions or potential locations. So we try to find another way. So we selected just one location of particle-strut connection. Since everything is symmetric, loading is symmetric, geometry, then we can expect that at all locations under certain deformation we will have the same very similar conditions. So we took, here is the application of coupled criterion, how it looks like. So this is the connection of the two strats, and we will now consider that the crack will have such a shape. This shape comes from the stress, from the equality of stresses along the potential crack faces. So this is in fact, this crack face is a stress isoline, which comes from the mechanical loading of the deformed structure. We have some fracture surface, or we can relate this fracture surface to a crack depth in this corner, or in this location. And we have to fulfill the stress and energy criterion, as has been said today several times, so I will go into more details. So both energy and stress condition must be fulfilled. So we calculate the stresses based upon the certain displacement. We calculate the change in potential energy upon the increase of the crack surface by a certain depth. And then we have crack length dependent values of sigma divided by sigma c and sigma incremental divided by g incremental divided by gc. So to this end we selected just one region or one part of the model. We selected just 1/8 of the model where two cells are connected, and here we model the real shape of the crack defined by the stress isolines which are there upon the mechanical loading. So we go further. So these are the stress isolines. This is the outer shape of the crack, and these are the stress isolines defining the crack shape. So we can have for every crack length A or crack size A specific surface of the crack faces, and we can calculate the change in potential energy caused by this crack increase. So here we applied a couple of criterion. So we loaded the foam structure by some displacement and calculated the energy release rate for different crack depths and also the stresses along the isoline. And this is the result. So here the load was not enough, so we have satisfied just the stress condition, but not for the energy one. So we have to increase the mechanical load further up to this point where both of these conditions are fulfilled. So here we fulfill the stress and energy condition, and this will be for us the crack initiation depth A. So when, in fact, we can say now that if the stresses in this depth, which is now around 13.5 microns, exceeds the strength of the material, the sigma c, then we can expect that the crack will initiate at this location. Once the crack initiates, we assume that it will propagate further and break the strut, because there is no mechanism which can arrest the crack or stop the crack. So this is the important parameter. So this crack initiation depth is very important. Since from this parameter we will then define fracture of particle struts. So we can go further. here are some numerical predictions of foam strands using this foam model. The procedure or the simulation procedure was the following. We started loading with some very small displacement. We check where is the high stress. We check in the depth of 13 microns what is the stress inside. If the stress was less than sigma c, we were sure that the fracture will not occur in that location. So if no place or no spots in the whole structure was found, the load was increased, the displacement was increased, and in such a iterative procedure, we check in every step we check all potential locations of failure. If the failure condition is fulfilled, if it was fulfilled, the stride was manually broken and calculated again. So in every step, only one stride was every time broken until the final fracture of the foam was received. And this is the final result. So this is the fracture surface of the foam compressed, and this is the result of the simulation. So this is the loading curve, force versus displacement or stress, which is force related to the cross section of the specimen. And you see that this maximum force, in this case, the strength of the foam, which is for us some characteristic. And if you take a look on the experiment, the structure was a little bit bigger, there was a bit more cells, so also the force is a little bit higher, but the stress is around 11.5 megapascals. So now let's summarize the result. So we compare different approaches and we compare how we can predict the strands of the foam using different approaches, including this which I present today. So in experiment we measured fracture stress about 11.5 megapascals. Then we tried to analytically estimate using these Gibson-Effie relations. Here we had difference around 19-20%. Then we tried also model the foam using some volume model. There was also not very good agreement. When we used the beam element model, the agreement was even worse. And the best agreement was found in case of this finite element model. We had different just around 7%, so it was for us really satisfying result. Okay, so we summarize work. So we predict the strands of the foam using the coupled criterion, or we use coupled criterion for selection of foam strands. The important thing is that we didn't use the coupled criterion for definition of breakage of heavy strata, but just for calculation of the break initiation depth, which we then applied in the simulation of the whole foam failure. Okay, and the agreement experiment fits very well, it's very good, so it was the main result. Good, so thank you for your attention.